Okay, the last one on here is like the strength of these covalent bonds, like which ones are hard to break, which ones are easy to break. So bond strength is also called bond energy, also called bond enthalpy. Remember, enthalpy is like the energy for a reaction. It's the energy required to break a covalent bond. Now, remember, covalent bonds, or any bonds for that matter, to break one, you have to input energy. Think of them as magnets. It's hard to break them apart. You have to actually put energy in to break them apart. So how much energy is required to break specific bonds? Okay. So for example, if I just want to break a chlorine bond, break one chlorine from another chlorine, it requires 242 kilojoules of energy. Notice that is a positive because it requires energy to break bonds. It is an endothermic reaction to break bonds. Now, a more complicated atom, so CH4, to break all of the hydrogens from the carbon, it's going to require 1660 kilojoules of energy. Okay, so note energy is always required to break a bond. Now, when you're thinking about a chemical reaction, right? Go to my reactants over here. I've got my products over here. What I have to do is I have to break some of the bonds over here and make some of the bonds over here. So the ones on the left, all the breaking of my reactants actually require energy. And the ones on the right, the actually making of bonds give off energy. So it's the difference between those two values of energy that actually give you the enthalpy, or the amount of energy for a full chemical reaction. So this is actually another way to calculate the enthalpy of a reaction, is by using what are called bond energies. So how do we use these bond energies in order to figure out the enthalpy for a reaction? Okay, so this kind of looks a little similar to something before, but it is different, so bear with me. So what you do is you calculate all of the energy it would be required to break all the bonds in the reactants. Okay, just do clean sweep, break everything, even if everything isn't broken. And then the amount of energy to make all of the bonds and the products. Notice the energy required is positive because I have to break these. And the energy over here in the products are the bonds made, so it's negative because they give off energy. So the actual equation for finding delta H using bond energies is the sum of all of the broken bonds, which would be the reactants, minus the sum of all of the made bonds, which would be the products. Notice this is backward from the delta H we did with delta H formations back in like module 5. Okay, so this is backward. So using bond energies, you do reactants minus products, because in reality, what we're doing is we're breaking all my reactants and making all of my products. So we can look up in this table and be like, okay, how much energy is associated with specific bond? And we can calculate, or really it's more of an estimate of the amount of energy that is associated, or the enthalpy for a specific reaction. So for example, number 7, I want you to determine the delta H for each reaction using their Lewis dot structures. So you have to actually know their Lewis structure because different bonds require different amounts of energy to break. For example, an oxygen-oxygen single bond only requires 142 kilojoules of energy. And an oxygen-oxygen double bond actually requires 498 kilojoules of energy. Okay. So I've got these two, we've got A and B, and also note that B are skeletal structures. And anytime I give you a skeletal structure, you need to finish the Lewis dot structure. Because remember, in our steps, you make a skeletal first, and then you got to fill in the right number of electrons. So if you want to try by yourself first, go ahead. And then I will go through the answers here in a second. Okay, so if you're looking at these answers, you did have to draw the structures to know what the bonds look like. CH4 is actually 4 CH single bonds, which takes 414 kilojoules of energy. And CCl bond, ClCl, requires 243 kilojoules of energy. So you add all of these, and then you subtract all of these guys. Well, I drew this out, C with 3 hydrogens and a chlorine. These bonds are all 414 kilojoules of energy. And this one is 339 kilojoules of energy. And this one is 431 kilojoules of energy. Hey, sorry. Okay, so it is reactants minus products this time, because these ones are all given off, they're negative, and these ones were all required, they were positive. So your answer So your answer is negative 113 kilojoules per mole. Now, if you did not get negative 113, you need to double check your signs, okay, and your order of operations. These multiply, then add all these, multiply, then add this. So it's this whole thing minus this whole thing. Okay, keep that in mind, especially when you do part B. So in part B, I drew out the entire structure. So if I have HCH, I actually needed a triple bond here to follow all of my rules for Lewis dot structures. If you wanted to like start over from the very beginning and do C2H2 and figure it out, you can, but this is a Lewis dot structure. I have two of them. 5 O2s. O2 is actually a double bond. 4 CO2s and 2 H2Os. Oh, I think that that H broke off. That should have been 2 HOHs. That should look like this. So these are the Lewis dot structures. So what I had to do is figure out all of the energy in these bonds and 5 of these, all of the energy in these bonds and 2 of these, and then do reactants minus products. Now, why did I have to draw the Lewis dot structures? Well, a CC single bond is different from a CC triple bond. So a CC triple bond is actually 837 kilojoules of energy. Same thing here, oxygen double bond is 498. So check your numbers and then check your math and make sure you get negative 2,428 kilojoules per mole, which means overall this reaction is exothermic. And I don't know if you noticed, but this is actually a combustion reaction, which we would expect to be exothermic because combustion reactions give off energy, right? It's fired. And that's how you get that negative 2,428 kilojoules of energy, is by breaking all of these bonds and making all of these bonds. So honestly, one of the biggest misconceptions that we get, especially if you take biology classes, are that breaking bond gives off energy. Like if you break off a phosphorus of an ATP, you get energy. And that's actually just way too simplified. If you're talking about an actual covalent bond, it requires energy to break a bond. However, usually there are a lot more parts of that reaction that accompany the breaking of bonds. You break these ones and you make different ones. And it's the energy of all of those changes together that give you the overall energy of the reaction. So while it does not require energy to break, while it does require energy to break a bond, for example, in the instance of ATP, there are other bonds that are formed during that process. It's a whole cycle. And overall, it could be an exothermic reaction. So you have to actually take into account the left side and the right side of a chemical reaction to determine if it's endothermic or exothermic. Okay, last thing here has to do with bond order and bond strength. Okay, we were talking about bond enthalpies up here. These are related to bond strengths, right? So if it's a triple bond, you might have noticed it's much stronger than if it's a single bond. And that actually is always going to hold true. The higher number of bonds or the more electrons that you share between things, the stronger that bond is. And actually, the shorter it is, they're closer together also. So down here with bond order is just the number of bonds connecting two atoms. Okay, this is a very easy, simple thing. It's just like how many bonds there are. So the bond order of the carbon-carbon bond in this molecule is 3. The bond order of hydrogen bonded to carbon here is 1. Single bond, triple bond, that's it. Bond order here in this molecule is a 2. Bond order here is a 1. It's that simple. Okay, now bond order goes along with bond strength and bond length. Okay, the higher the bond order, or like triple bond versus double versus single, higher bond order means it's going to be a shorter bond. Okay, so if it's a triple bond, it's shorter and it's stronger. So I was using nitrogen as an example a moment ago. I pulled down actually their energies. This one, it had a higher strength. It was harder to break this bond. I also said it has to do with bond length. So I'd be like, okay, this is bond order 1, single bond versus double bond order 2 versus triple bond order 3. This one is stronger. This one is the weakest. Also, bond length-wise, the bond of this, or the length of this bond is 1.47 angstroms, whereas this one is 1.24 angstroms, whereas this one is 1.10 angstroms. So the nitrogen triple bond is both the shortest and the strongest. And again, this will always hold true for single versus double versus triple bonds, called bond order. Okay. Now, Well, how do you calculate the bond order of something that has a resonance structure? So for example, in this SO2 molecule, I would say, well, this has a bond order of 1. This SO bond has a bond order of 1. And this SO bond has a bond order of 2. So what's the bond order of the SO bonds in this molecule? Well, it's the average of 1 and 2. It's 1.5. So we would say this has a bond order of a 1.5. And its strength would fall somewhere between a single bond versus a double bond. All right, same thing over here. I redrew this benzene molecule, C6H6. If I was talking about all of the carbon-carbon bonds, their bond orders, well, I have a 1 and then a 2 and then a 1 and then a 2 and a 1 and a 2. So the carbon-carbon bond order for this molecule would be 1.5. You just average the carbon to carbon bond orders. That's it. So it's got resonance. It's probably going to have a weird bond order. Okay. Also, again, if it's got a bond order of like 1.5, it's stronger than a single bond, weaker than a double bond. So the bond enthalpy or energy will change accordingly.